This meeting is being recorded.
এইটা কেন আসছে? এটা কখনো আসে না। হ্যাঁ, আমাদের এইটা একটু
বড় আছে এটা
কি এটাকে সরাবো? ঠিক আছে।
कार्ड स्पेस नहीं है तो स्टॉप
Okay, so it's a pleasure to have Professor Amitabha Lahiri from the SNBO Center as our colloquium speaker today. Professor Lahiri did his undergrad at the Ashford Presidency College, as many of our colloquium speakers tend to do. And he did his PhD from the Syracuse University in the US and postdocs from Los Alamos National Lab in the US and University of Sussex. And then he came back to India and became a faculty member at the SNBO Center, where he has been since then. Professor Lahiri's expertise is quantum field theory in various situations, like field theory in the curved space-time, as well as various applications of various gauge theories. I was just looking through his recent papers. One thing that caught my eye was he has shown that inertia is generated by space-time geometry. So that seemed very interesting. Although today's talk will probably not on that, but well, partly maybe.
in the end.
So and also since we have a memorandum of understanding with the SNBO Center, so we have many collaborations, not research collaboration, but we have. Well, our students do projects. So some of you may go and do a project with some of the faculty members there next year. And also one of our students is currently doing a project there. From the recent batch, there were two students who were doing. That's right. So one of our PhD students, Professor Taposh Bagh, there is a co-advisor. So we have, it's one of those, institutions who are very, very close and sort of a sister brother institutions to us. So we are very glad to have Professor Lahiri as the speaker today. So
Thank you, Ritavan, and good afternoon, everyone. So I'll speak in English. That's how I prepared. This is a talk that I have never given before, and also this audience is somewhat different from the usual audience that I have for my talk. So I had to prepare it somewhat differently. So what I'll talk about is based mostly on quantum mechanics rather than on anything else. And so this is all standard stuff. And so only the last slide will talk about my current work and where it is going. So basically, the problem is, I have called it the solar neutrino problem. The talk, I think, forget what the name actually was. The solar neutrino problem is something about missing neutrinos. This problem has been known for something like more than 60 years, nearly 60 years. Now, most of you know what neutrinos are. They're particles which are conjectured by Pauli to account for missing energy and momentum in beta decay, in nuclear beta decay. So they found that when a neutron decays, basically when a nucleus decays, you find a resulting nuclei and you find the beta rays, which are basically electrons, but that did not balance the total energy and momentum, and they couldn't find anything else that could actually carry away the energy and momentum. So Pauli conjectured, Bohr actually conjectured that maybe energy and momentum are not conserved in nuclear decays. They didn't know it was called weak decays then. So Pauli thought that was completely ridiculous, and he was right, of course. But Then he conjectured that there was another particle called the neutrino. Neutrino means small neutron, basically. So neutrino, which carried out the energy and momentum, which was missing from the measurements of nuclear beta decay. And so John Updike wrote this poetry about neutrinos. It's actually a long poem, and I just took the first stanza. So neutrinos, they're very small, they have no charge and have no mass and do not interact at all. So this is why they couldn't be found, because they do not interact with anything. They do not have any charge, they do not have any mass. So they're not like any other particle that we know. Okay, so we cannot actually see them because they do not interact with our retina. So you do not see them. So they have a very weak interaction with electrons and maybe protons and neutrons, but that interaction is so weak that it's very hard to see. And the Earth is just a silly ball through which they simply pass, like dust meets down a drafty hall or photons through a sheet of glass. So it's just transparent to neutrinos because they do not interact, they go through. That's why they are very difficult to find. So Pauli conjectured them in 1930. So he did not give a talk about this. He did not write a paper. He wrote on the back of a postcard and sent it to a meeting saying that I think this is what happens. Okay, and of course, that is actually what happened, but it was never published in anything. And people thought about this and realized that it could be right. And so they started looking for it. And this discovery took 26 years because it was very difficult to find. And Common and Rhines got a Nobel Prize in 1995. That was another 30 years, 40 years, 39 years. Okay, and Kavan did not get any. Kavan was already dead. Kavan died in 1975, okay, or 76. So Rhines got a Nobel Prize because I think I read somewhere that Rhines had spent the maximum time, looking at neutrinos or looking at one particle. The maximum time compared to any physicist looking at one particle all his life. So Rhines got Nobel Prize in 1995, and muon neutrinos were found in 1962, which was very soon after. The first one was antineutrino. In 1956, the neutrino itself, the electron neutrino, was found after the muon neutrinos in 1965. I forget who
After antineutrino was found.
Yes, because that was because it's neutron decay, right? Neutron decay is proton, electron, and antineutrino. So they found the antineutrino. So with muon also, they found the muon antineutrino.
I mean, they are not even very different. Charge.
Well, yes, it's chargeless, but the issue is about chirality. But anyway, so they found antineutrino. And anyway, so muon neutrinos were found in 1962, and that was Lederman and some others. So they got a Nobel Prize in 1988. So that was again a long time. Tau neutrinos were found in 2000. They did not. And these neutrinos were always found in decays involving charged leptons. So the electron neutrino is found with the electron, the muon neutrino is found with the muon, and the tau neutrino is found with the tau particle, with the tau lepton. And so it sort of worked out that they are all partners of this charged lepton. So these uncharged particles are partners of charged leptons. Like, it's actually very similar to saying that nucleons are, I shouldn't even say nucleons, I think they are called nucleons, right? Neutrons and protons, they're like particles, right? So neutron is charge 0 and proton is charge 1, but other than that, there is very little difference between them. There is a difference in mass, and that mass is something that nobody can explain. Okay, that difference, that is something that is still there. But other than that, it's very similar. They're very similar. And similarly, for these leptons, there are charged leptons and uncharged leptons. Charged leptons are these electrons, muons, and tau particles, and uncharged leptons are the neutrinos. Oops. Where did I go? I need to go back.
Yes.
Right. Right. So you can see that I prepared this in a hurry, so I forgot to do this by stages. I finished this last night at 11:30. So anyway.
So I should mention that Professor Lahiri started from Purulia early morning today.
Yes.
And then
5:30 in the
was
morning.
taught a class and then came to this talk. So additional thanks to him
Yes.
for doing this.
It's okay. I have never done this before, so that is exceptional for me as well. So anyway, so you can see how weak the interaction is. There are 7 times 10 to the 10 neutrinos passing through each square centimeter of our body, okay, through the earth, and that's a lot of neutrinos. It's not a lot if you think about it. I mean, you are dealing with Avogadro numbers all the time, right? Gas and everything. But you can see those things. You can feel the pressure. You can sort of see if you have 10 to the 23 electrons, that's going to be a thick beam. Okay. But this is not like that. This is just passing through every square centimeter, every second. And we still don't see anything. Okay. And it's very difficult to measure them. And these neutrinos are mostly from the proton-proton interactions in the solar core. That is where our energy comes from. Most of the sun's energy comes from there. Protons interact to form a deuteron. So it's like the inverse beta decay. So it goes from one proton becomes a neutron, and that becomes a deuteron to proton plus proton. So that creates a positron and a neutron. Okay, and the energy that produces is basically most of the energy that the sun produces. That's like 90% or something. I think Amitabha and Suchetana are more of an expert for these things. And these things do not have any electric charge and they have vanishing mass. So only weak interactions are there. Weak interactions literally is true. It's 10 to the minus 5 strength compared to electrical interactions. So those interactions are very weak, and because they do not have any mass, we do not actually feel them. We do not feel them hitting anything. Okay, so they're very difficult to measure. And this super Kamioka neutrino detector experiment, super Kamiokande. So there, the super Kamiokande 4, that is the current one. Their detection rate is 15 per day. I think their size is something like 3,000 tons of water, maybe more. It's a few thousand tons of water. I forget. It's a huge number, maybe bigger than 3,000. It's probably 200 meters cube or something.
It's like an auditorium full of water.
Yes, it's like 200 meters cube, bigger than an auditorium. It's bigger than it's like a football field and standing up. Yeah, something 50 kilometers, 50,000. Okay, so that's a huge amount of water, and that water has protons and deuterons and some tritium as well, and that interacts with the neutrinos, and that is how they are found usually. And with that much water, with that many atoms in there, that many protons, we still get only about 15 a day. Okay, and so these. But still, solar neutrinos have been detected for a long time. They have been people have been detecting them since the early 1960s, and that is the Homestake experiment, for which Ray Davis Jr. Ray Davis 3, Ray Davis Jr. Well, he decided to know. See, he did some work for the army. Then I think he joined Bell Labs or something. And then he asked for a problem that said that would make him think. So, he didn't actually ask. I think he tried to find a problem that would make him think. And so he decided to pick on measuring the neutrino flux. And then he found, he spent his life doing this and got a Nobel Prize out of it. So then he found that the number of neutrinos, he actually measured neutrinos. He found that he could find neutrinos, but the number of neutrinos that he found was quite a bit less than what was expected from the number of reactions that are going on inside the solar core. I mean, that you can estimate. That number you can estimate by the energy that we get. We know how much energy this proton-proton interaction is giving us. So we know how much energy we are getting from the sun. There is a fairly good solar energy model that sort of tells us how many interactions are going on. And so we know what is the number of neutrinos that are being produced in the solar core. Then we can calculate. It's like, this usual Gauss law 1 by r square kind of calculation. And we can calculate how many neutrinos should be hitting the earth. And that is what is said 10 to the 10, around 10 to the 10 neutrinos per square centimeter. And he found that it's still missing. Okay, number of neutrinos is missing. Number of neutrinos is less than what was expected. So the expected number of events, this can be calculated from the standard solar model. As I said, the luminosity is determined by the number of reactions. And what they found, what Ray Davis found, was that the observed number was only about 1/3 of what was expected. And I think it was John Bacall who figured out that the number is actually what the number should be. He looked at the solar model, he calculated the number of neutrinos that should be there, and found that the observed number is 1/3 of that. And this is the solar neutrino problem. Okay? So this problem, I would say, was unsolved for a long time. Even though people had some idea of how to solve it, it was still, there was no proof of that, so to speak. This 2002 is Ray Davis Jr. with others. So Ray Davis Jr. got a Nobel Prize in 2002, and his measurements were in the early 1960s. And I think around 1967 or 69, he first concluded that the number of neutrinos is less than it should be. Okay, and John Bacall did not get one. So did John Bacall?
No.
John Bacall did not get
The
one.
others, I mean, it was confirmed after Kamiokande also found the same
Right.
number. So then they took
Right.
from Kamiokande and Ray Davis, they got.
Snow also that collaborated with snow result and.
Yes,
data.
yes, yes.
It was in 2002, I think
Ray Davis
the.
Jr. was
So for the
2002.
problem, 3 people got, and then for the solution, 2 others.
Bacall did not get one, which was a bit okay, odd. But anyway.
I'm not sure.
Yes, he,
Michael probably passed.
in 2002?
I don't know.
I don't think so. I don't think so. No, I think it was after 2002. So people were expecting that he would get it with Ray Davis Jr., but he didn't. But he was the theoretician, right? So the 2002, I think, was only the experiment. Okay, so I'm going to talk about the theory behind this, how to explain this solar neutrino problem, how to find the solution and explain it. So what I'm going to say is basically, based on with the Lagrangian point of view, but most of you have not done quantum field theory, so I'm going to skip the Lagrangian point of view, and I'm going to talk about only the equations. You have seen equations, yes, you have seen Schrodinger equation and similar things. So I'm going to talk about the equations, and even if you have not seen Dirac equation, you will probably see it very soon. So that is what I start with. So this first one is the Dirac equation, and we have the Dirac. Suppose I have two free fermions. Okay? Two free fermions, masses are different, mass m1 and mass m2. So they will satisfy the Dirac equation. I'm saying I'm taking the wave functions of these two particular fermions, what I'm going to say now also works for the Schrodinger equation, the non-relativistic Schrodinger equation, but I'll write Dirac equation because that's what they satisfy. Okay, so if you have any questions, please ask. Okay, even if you are unable to follow what I'm saying, then please ask. Okay, because I don't know whether you are following or not. You are looking at me, I have no idea whether you are listening or whether you are falling asleep or whether you are just not, getting into it. So if you have any questions, please ask. So I have no problem stopping and explaining. I don't have very much there. I think it's going to be a very short talk. And so if you ask, it will go on for an hour. Anyway, so if I look at these two equations, you know that in quantum mechanics, we say that the wave function can be multiplied by a phase, e to the power I theta. That does not change anything. So I have these two equations. So these two equations also I can multiply by independent e to the power I theta 1 and I theta 2, and both of them remain invariant, right? Theta is constant, so it just comes out. Whatever I multiply it by, it will just come out. And of course, functions can be multiplied by a phase, so I can always do this. So it says that these are independent U1 transformations. U1, if you remember your group theory, I don't know if you have studied this, MSc you should have. And U1 is basically e to the power I theta, okay? Elements of U1. So if the two masses are the same, M1 and okay, so applied group theory. Right. So if the masses are the same, then I can write these two equations together as a doublet, okay, like a matrix equation. So this is a column vector, and I write ID / minus m. I have the two wave functions. Okay? This is 0. Now, this equation is invariant under an overall multiplication by a number again, and again I can multiply by e to the power I theta. But this is also invariant under more general transformation by a U2 matrix. U2 is a 2 by 2 unitary matrix. Okay, U dagger U is 1. I don't know if you have studied that today. Okay, so you have studied that today as well. So that's very good. So it's invariant under a more general transformation by a U2 matrix. Okay. And what does the U2 matrix do? It takes this column vector and mixes the two, right? It's a 2 by 2 matrix, so it mixes the two things. And this invariance is a starting point for weak interactions. And using lepton doublets that we mentioned earlier, this neutrino and electron, neutrino and muon and so on. But we are not going into that. I mean, I thought about talking about that, but that is not the focus of my talk. I'm not going into there at all. I'm just mentioning that U2 is quite familiar to people who are going to do particle physics, because your weak interactions, theory of weak interactions start from U2, and if you have SU3, then you get theory of strong interactions and so on. But here, I'll just stick to these neutrinos now. Any questions? Okay, so what I want to mention is a kind of flavor mixing for neutrinos. The reason I mentioned the U2, okay, it's just a sort of trick to make you think about mixing. Okay, so it's just there are two fermions, then you have a U2 transformation. And now I have 3 types of neutrinos. So suppose for a moment that they all have the same mass. Okay? And then I can write them in a triplet, like a column vector. Okay. And they will also satisfy, each of them satisfy the Dirac equation when they're free. Okay. And for 2 particles, so 2 wave functions, I had U2 transformation that left it invariant. And now I have U3, right? This kind of transformation, psi prime going to U times psi, this U will be a 3 by 3 unitary matrix. Okay. So this is just a complex 3 by 3 matrix. And we say that it's U3, and U3 is SU3 cross U1. So that you may not know right now. But basically what this means is that U3 has determinant. If you take a 3 by 3 complex unitary matrix, the determinant is a phase. Okay, because when you take U dagger U equals 1, you take the determinant of both sides, you get that U star times that U equals 1. Okay, so that means determinant of U is a phase. So you can take the phase out. You take the phase out, 1/3 of the phase comes out as common, and then the remaining matrix is determinant plus 1. Okay, so that is called an SU3 matrix, and the phase is basically U1. So that I call it SU3 cross U1. And this mixes these 3 wave functions, right? So this mu1, mu2, mu3, whatever these neutrinos are, they are going to get mixed by this 3 by 3 complex matrix, right? If you have a 3-dimensional vector in space and you apply a rotation vector, then you just mix their components, you mix the components of the vector, right? That's like rotating the basis. So here you have a complex 3 vector, and we have a complex 3 by 3 matrix, which does the same thing. It mixes up. Okay. U dagger, you keep that in mind. We don't need that right now, but it's basically mixing up these things. Okay. So these 3 are getting mixed up. And so you could say that this U matrix, this U3 matrix, this causes a rotation in complex 3D space. Right? That's exactly what we are doing. The rotation, of course, not in real space. This is a complex vector space. Okay, 3 3-component complex vectors. And then we can say, so we can say that this U matrix mixes the neutrino flavors. Okay, so by flavor, I mean whether it's electron or muon or tau and so on. So, or 3 types of neutrinos with the same mass in this case. So we say that this U matrix mixes the neutrino flavors. Again, I have only shown this to sort of get you used to the idea of mixing. Neutrinos do not have to have the same mass. I mean, I can always write 3 wave functions like this if they have approximately the same kind of properties, not necessarily the same mass, but I can always write this and multiply this by a 3 by 3 matrix, and then I'll say that they mix, right? I don't care whether what mixing causes, that comes later. But I can always write this. I can make this operation and say that it mixes the 3 components, right?
So just a quick, maybe a naive question that, is it known that why we have three family of leptons?
No,
Not known.
no. There is no,
Why not two, why not four?
No, no, two it has to be, the one it cannot be because then I think. Some
Violation.
identity is violated.
so those are the anomaly
And
conditions.
those are annually ones.
So there is an anomaly condition which basically says that it has to be three. No, it has to be three. But people have looked at this thing with 4 and 5 and it's not completely ruled out. But then again, how many dimensions do you have? You ask a string theorist and they'll say you have 10.
Yeah,
So
but because sometimes people talk about this other species of neutrino, the
Sterile
sterile species,
neutrino.
yeah, the sterile.
sterile comes because of neutrino masses and I think there is more of an expert on those things. But anyway, so but sterile neutrino comes because we do not see right-handed neutrinos in nature.
Right.
So you figure out that there is some other species of neutrinos which only comes as right-handed or something. Okay, so
So that is the reason.
yes,
for-
but nobody has seen anything like that. And whether they're actually observable, I don't know. Okay, so that's still an open question. Anyway, that is not necessarily a new generation.
Yes.
Yeah.
Yeah, so I have just one basic question. When you said the U is basically causing the rotation of due to the U is basically causing this mixing of the flavors, right?
Yes.
Yeah, so when we have unequal masses,
Yes.
this unequal mass components, they are not affecting this rotation anyway.
I'm just mixing them. I'm just writing this. I'm not doing anything. I'm not claiming that they are giving you something different. It's mixing, right?
Yeah.
I write this. I'm not saying that the mixed thing is something.
So that remains kind of a constant.
No, I'm not saying that it is something. I'm saying that you are mixed with that person. That does not give me anything. I multiply you by 3 and multiply him by 4 and add by divide by 7. Right? I'm just doing this. I'm just saying that I mixed this. This is the way of mixing. Okay. It's an operator.
Is there any kind of condition where I cannot do?
No, I can always do. I have a vector, I have a linear operator. That's
I
it.
can always do that.
I can always do that.
Nothing particular about neutrino
Nothing.
in this case.
Absolutely nothing. The only thing that will actually, where your question is relevant, is when I say that I mix and get something physical.
Yes.
That's when the real question is. What do I get? Is that the physical thing? Here, I have not claimed anything as yet. Okay. So, as I said, you can see the last line. The equation of motion will not be invalid. So that is not a physical thing as yet. Okay. So I had free particles at free fermions. They had equations of motion that made them physical. If you have a particle with a mass, you have the equation of motion. That's a physical particle. When I mix them, that is not necessarily a physical particle. Okay, I would say it's not a physical particle. Okay. So the solution of the solar neutrino problem comes from here. That we say that neutrinos with well-defined masses do not have well-defined flavors. Okay, now I have to be careful about what I say. You have to be careful about listening to this. So we mentioned 3 different flavors: the electron neutrino, the muon neutrino, and the tau neutrino. Okay, these are flavors. These occur in these doublets, these lepton doublets with charged leptons, which means that there are interactions where the electron and say antineutrino are created together. For example, in the neutron decay. Okay, so in muon decay, you might find an electron is created with a muon neutron. Okay, so things like that will happen. So you have a process in which there is a muon that breaks into an electron, an anti-electron neutrino, and a muon neutrino. Okay, so there are all these balances that things are getting balanced. So wherever there is a muon, there has to be the process that some kind of neutrino will come out. But those things are not physical. They do not have well-defined equations of motion because they do not have well-defined masses, because I have mixed. That is the solution. The solution is that there are states of definite flavor, electron, muon, and tau. There are states of different masses, definite masses. So I call them M1, M2, M3. So both mass and flavor are observables. That doesn't mean they all commute with the Hamiltonian. Okay. So they are observables, which means the eigenvalues of the observables will provide orthonormal eigenvectors. You know this from quantum mechanics. So the eigenvalues of the masses, where you have M1, M2, M3, they will give you three eigenvectors, which are all orthonormal to one another. So M1 does not mix with M2. I mean, M1 is orthonormal to M2. The flavors are also observable. So the flavors will also give you orthonormal eigenvectors. So one flavor is orthonormal to another flavor, but the flavor and the masses are not the same. Okay. So what that means is that there is a mass basis and a flavor basis, and these two are related by this U kind of rotation. It's a electron neutrino, muon neutrino, tau neutrino. ইলেকট্রনের সঙ্গে আসছে ইলেকট্রনের সঙ্গে আসছে ইলেকট্রন নিউট্রিনো। যখন আমার একটা নিউট্রন ডিকে হচ্ছে তখন আমার একটা প্রোটন আসছে, একটা ইলেকট্রন আসছে, একটা অ্যান্টি ইলেকট্রন নিউট্রিনো আসছে। যখন আমার মিউন ডিকে হচ্ছে তখন মিউনের থেকে আমার নেগেটিভ চার্জ আসতে হবে, মিউন থেকে ইলেকট্রন বেরোচ্ছে, তার সঙ্গে আমার একটা অ্যান্টি ইলেকট্রন নিউট্রিনো বেরোতে হবে আমার লেফটন চার্জ কনজারভেশনের জন্য, লেফটন নাম্বার কনজারভেশনের জন্য। আরেকটা বেরোতে হবে, সেটা হচ্ছে মিউন নিউট্রিনো, আমার মিউন লেফটন নাম্বার কনজারভেশনের জন্য। ওকে, মিউন থেকে আমার সেই জন্য যখন মিউনটা ডিকে করছে, আই গেট an electron for the electric charge, an anti-electron neutrino for the electron lepton number, and muon neutrino for the muon lepton. So that is the flavor. The electron neutrino, muon neutrino, tau neutrino. These three are the flavors. Types. But the flavor is important. What flavor means that they take part in weak interactions. I'll come to that. So this flavor eigenstates are what take part in weak interactions. So whenever you create these neutrinos by some interaction or by a decay, they're created as flavor eigenstates. And those things are orthonormal. So if you are creating an electron neutrino, that does not have any projection to a muon neutrino state. Okay, so those are orthonormal. But once they are created, they propagate as mass eigenstate, because Hamiltonian is mass, right? Hamiltonian is energy. So they have to propagate as Hamiltonian eigenstates, and that's where the mass eigenstate comes in. But mass is a mixture of the different flavor states, right? So they propagate, and after a while, and I'll show you how to do this. After a while, if you measure them again, they may not remain in the original flavor state because they have mixed. And if the rotation has proceeded with time and they have mixed more, it may not be in the same mixture that was there originally. It's not necessarily the same linear combination, right? So it may be a different linear combination, different mixture, and you'll find something different. So
We can express the mass eigenstates in the flavor basis and the flavor eigenstates in the mass basis.
I'll do that in the next slide. So here, so this is what I said.
That is mixed.
Yes, Hamiltonian is diagonal in the mass basis, and weak interactions are diagonal in the flavor basis. Okay, these two are different things. Any question? Any other question? Okay, right. Right. So now this is the mixing. Okay, so I can write the flavor states. So here I am writing, typically how I do in quantum mechanics. So I have the only thing is that there is a bit of a degeneracy in the symbols. So this new one, ket, is the vector, the basis vector, and new one is the coefficient. Everybody does this, and this is extremely confusing. Okay, so this is the first thing that I just figured out when I was writing this talk, that I have not fully understood this. So this basis vector and the coefficient are given the same symbol. I mean, people run out of symbols very quickly. There are so many particles, right? So, I mean, you have to introduce the Bangla, the Nagari after a while. So other than that, you have this. So these are the coefficients. These nu e, nu mu, these are the coefficients. Nu1, nu2, these are the coefficients. So I have this in the mass basis, I write them as a linear superposition. And in the flavor basis, I have a similar thing with basis of nu e, nu mu. Exactly. This is the 3x3 matrix that gives you a mixing. So I start with, I look at this components in the flavor basis, and what I say is that they're result of a unitary transformation from the mass basis. Okay, so this is what it looks like. So explicitly, and we can write it like this. This is just that, and this is just a parameterization issue. So you have to remind me of the time. Okay, I think I'm going along with the mails. Okay. So this 3 by 3 unitary matrix needs 9 real parameters. I'm not going to work this out. You can work this out yourself. It's unitary. So once you put the unitarity condition, there are 3 conditions on the diagonal and 6 conditions on the off diagonal. So there are total 18 for 9 times 2 complex numbers. And so 18 minus 9 is 9. So you're left with 9 real parameters, which are all angles. U3 are all angles. They are not open parameters. And so angles means that you can write them as phases, right? And remember that whenever you have a transformation like this, each of these are basically coming from wave functions. And wave functions are defined up to an arbitrary phase, right? So I have 6 wave functions here, 3 on the left and 3 on the right. I can take out one common phase from all 6 of them. I'll be left with 5. Okay, so those 5 are observed in the wave functions. Okay, so from the 9, 5 are eliminated because they're observed in the wave function. So 4 phases will be left. So 4 parameters will be 4 real parameters. All of them are angles will be needed to parameterize this 3 by 3 complex matrix. Okay, so these 4 angles are called theta 1, 2, theta 1, 3, theta 2, 3, and delta CP. They have certain meanings. We are not going to go into that in this lecture, but basically, I should mention only one thing, that this delta CP is related to, it's a measure of the CP violation, okay, charge parity violation. Violation by charge parity symmetry. We are going to sort of focus on 2 flavors of matrix, 2 flavors of neutrinos for simplicity, because I want to show you how these things are calculated, and that is best done in 2 flavors. So for 2 flavors, this U matrix is just 2 by 2, as I mentioned earlier. Okay, and in that case, I have 4 real angles because 2 by 2 complex is 4, and again, it's still angles. Okay? This U2 is a, what is called a compact group. So that's those are angles, and you have 2 on the left and 2 on the right. And as I said, you can take out a common phase, and then you'll have 3 phases that can be absorbed in the wave functions. So only 1 angle is needed. Okay, and that is basically the same as a rotation matrix in 2 dimensions. Cos theta, sin theta, minus sin theta, cos theta. Okay. Any question? I'm speaking too much. So if you have any question, maybe I'll have some time to stop.
Maybe this rotating away the phases, I have to take another class or half a class.
No, it's quantum mechanics. It's not in group theory.
Yeah.
But compactness is issue 3. I think you should say something in a class. Okay, why is it compact? Why are they all angles? I think that is important. So, okay. So we talked about I wrote the rotation matrix for the components of the wave function. You can also write them in terms of the basis. This is convenient to write in this case because I want to show you how to calculate this. And most okay. This is different from what we wrote in the paper. So I'm just following a slightly different convention. I will discuss it with you afterwards. So for basis states, we have this. Okay, so you can. I'm not going to work this out, but basically what this means is that the vector remains invariant. The vector is something that is objective in the sense that you make a rotation of the basis states and you make a rotation on the components, and you can do that simultaneously, but the vector will remain invariant. Okay, so not the vector itself. So it's like saying I have a vector, right? I'm not rotating the vector, I'm rotating the basis, and then the components of the vector in the new basis are different, but the vector remains the same. So I can write them. So I have a vector, say call that vector V. So Vx, Vy, Vz, and I have Ex, Ey, Ez. Okay. So I make a rotation, I call it E prime X, or Ex prime, Ui prime, Ez prime, and I have three new components, Vx prime, Vy prime, Vz prime. So that Vx, Ex plus Vy, Ui plus Vz, Ez is the same in the new one. But what does that mean? That means if I write that as a matrix, I have to have inverse operations. Okay, the one, if I write Vx, Vy, Vz as a column vector and rotate that with a rotation matrix, and I write E1, Ex, Ui, Z again as a column vector and do that as a matrix rotation, then the two rotations have to be inverses of each other, right? But think of the vector as something objective. Vector is not something that, that changes simply because you change your basis. Okay, you change your basis, that is just a measurement thing. I have x direction this way, you have x direction that way. That does not mean that, some motion is different. Okay, so it's like that.
Actually, in rigid body dynamics, when you want to write the rate of change of a vector from the body frame versus the lab
Oh,
frame,
Baba. Yes.
that's the exact thing that.
Yes, anybody who does that without looking at notes is absolutely respectable, whatever they say. That's unbelievable. I mean, I just remember that, in presidency, there used to be, in the old presidency library, there used to be a book by Whittaker, Analytical Dynamics, about this thing. I think it was like, I don't know, 500 pages with 3 diagrams. Okay, and he explained Euler angles in 3 pages without a diagram. And I read that. So it took me like a week to understand what he was saying.
Really analytical.
Yes, analytical. Analytical is right. I don't know why they didn't draw the diagrams, probably because they had to pay a draftsman to draw the diagram. That's why they didn't. Anyway, so, right. So we make this transformation. So this is actually the inverse of what we had for the components of the vectors. So we had U, now we have U dagger. So in the mass basis, the mass basis is given by the nu I kits, and the flavor basis is given by the nu alpha, right? And the mass basis are diagonal, they are the eigenstates of the Hamiltonian. So the Hamiltonian is diagonal in that basis. So the stationary states are just e to the power minus IET for each mass eigenstate, right? And EI will be P square plus MI, right? P square plus M1 square or what. Right. So when I look at the flavor state as time dependent state, I'll find that this mixture, this I shouldn't call it a mixture, this transformed state is what gets into describing the flavor state. And so if I want to look at what the flavors are after a certain time, I evolve this to some time t and look at the projection on each flavor. Okay, that is my transition amplitude. That is what your quantum mechanics says. And so I take the mod square and it gives me the probability. So the probability of finding a neutrino of type beta, if my original neutrino is produced as type alpha, is this. Right? So ordinarily, if I'm looking at the solar neutrino, it's produced as electron neutrino. And when it comes here, maybe I can find muon neutrinos and tau neutrinos, and maybe not all of them are electron neutrinos. That is the solution, the solar neutrino problem. So if I start with this all neutrinos, I start by saying that all neutrinos are all the different mass types of neutrinos are produced with the same 3 momentum, which is what you would expect. You have a process going on and something comes out, they have a 3 momentum, which has to be the same because of momentum conservation, but the masses are different. That's why the energies are not necessarily different. Okay, so I'll get this p square by plus m square square root, and then you consider all neutrinos to be ultra relativistic because they're all very fast. The masses are extremely small. So if they're ultra relativistic, I can break them up in this form. So there is some E overall average E, which is this mod P is some basic energy, and then the each of the types of neutrinos, each of the mass types, can be witness this.
And
And
there's one thing
yes.
you mentioned that they get uncomfortable with what I found.
Oh, okay.
Is that if you don't put H cross there, so you say that H cross is equal to one.
Oh, yeah, absolutely,
Equal to
absolutely. Yes, you are right. You are right. This is what
Okay,
happens. When I make a
Very
talk late at night.
uncomfortable
Yes,
with one
absolutely.
cross.
You are absolutely right. H bar is one.
Also equal to one.
H cross is equal to one.
C
C is one. Yes, I think they know C.
Yeah, C is one, I think they are.
C is one. This is 1 nanosecond. Okay, you know. So you know that, right? This is 1 nanosecond. So C is one. This is length. I mean, this is 1 nanosecond.
One is length is the.
Length is time. Time is length. Nanosecond is 30 centimeters.
Yes.
So 1 foot. 1
এক
foot.
feet হয় হচ্ছে 1 nanosecond.
One.
তাহলে আমি 10 বললাম, আমি 3টাকেও 1 করে
You are an astrophysicist. So this is what astrophysicists do. Be careful. Be very careful. The age of the universe is giga years. Doesn't matter how many. Okay? So everything is in parsecs. Parsecs and light years are the same. So anyway. So then in the mass basis, I can write the Schrodinger equation like this. In the mass basis, the Hamiltonian, the free Hamiltonian is diagonal, right? So only the free Hamiltonian, I'm simply writing the free Hamiltonian for the two neutrinos in the mass basis. So I can write it like this. Right? Everybody agrees with this? They can go to the next one. Any question? Sorry? I have not done any alpha beta at this moment. এটা হচ্ছে মাস বেসিসে, কারণ ফ্রি হ্যামিল্টনিয়ানটা ডায়াগোনাল এখানে। এই যে শ্রোডিঙ্গার ইকুয়েশনটা আমি সবসময় ডায়াগোনাল ফর্মে লিখতে পারি। হ্যাঁ, আলফা বিটা আনতে হলে আমার হ্যামিল্টনিয়ানটা ডায়াগোনাল থাকবে না। ফ্লেভার ইলেকট্রন মিউ1 হোয়াটএভার আই এম ডুইং উইথ ইলেকট্রন এন্ড মিউট্রন। ঠিক আছে, ওটার মাস বেসিস না, আলফা বিটাটার মাস ফ্লেভার বেসিস। ওকে, আমি দুটো বলার বুঝতে সহজ হবে বলে, তিনটে লিখলে অনেক বড় হয়ে যাবে, যেহেতু এখানে মানে আমার প্রথমত জায়গা কম লাগছে, তিনটে হলে আমার এক্সট্রা স্লাইড ব্যবহার করতে হতো। আর আরেকটা হচ্ছে যে আমার একটা প্যারামিটার আছে, আমার যদি প্রত্যেকবার 4টে প্যারামিটার লিখতে হয় প্লাস তার ভিতরে কয়েকটা কমপ্লেক্স থাকবে, একটা অন্তত কমপ্লেক্স থাকবে, আর একটু বেশি প্রবলেম হবে, জায়গা বেশি লাগবে, এটসেট্রা। তখন তুমি জিজ্ঞেস করবে যে 2-1টা এরকম হলো, 3-1টা কিরকম হলো। হ্যাঁ, তখন একটা দিয়ে আমার আপাতত কাজ চলে যাচ্ছে। So the flavors will occur when I look at, oh, wait, go back here. Have I done this? Okay, so this was the free Hamiltonian. So after the free Hamiltonian, I have to talk about interactions. So neutrino interactions are always going to be weak interactions, and they will be interacting only with other electrons or protons or neutrons in matter. Okay, in other complicated cases, there may be other things. So neutrinos in matter will have electroweak interactions with electrons, protons, and neutrons, and they do that. I have not drawn the diagrams because again, I ran out of time and didn't have time to draw these pictures. So they do by exchange of charged or neutral gauge bosons. I don't know if you have done field theory, maybe you have not, but if you do, you will know that all interactions proceed by exchange of bosons. Okay, not exchange of elements, exchange of bosons. Okay, so particularly exchange of gauge bosons in most cases, and like electrodynamics is done by exchange of photons. Okay, and strong interactions proceed by exchange of gluons, and weak interactions are done by exchange of charged W plus minus bosons or neutral Z bosons or photons. Okay, so because this is electroweak, this electroweak theory is what Weinberg, Salam, and Glashow got Nobel Prize for, and this was sort of the major unification after Faraday. Faraday unified electricity and magnetism, and this electroweak theory, they unified weak interactions. Not exactly unified, but basically they said that all these particles have the I could write the interactions of all these particles in sort of the same, using the same gauge bosons. So these gauge, there are two kinds of gauge bosons, neutral gauge bosons, the Z and gamma, and this W plus minus charged gauge bosons. You have one is the antiparticle of the other. Anyway, so I'm not going to go into that very much, except saying that at low energies, I can write this as an effective 4 fermion interactions. So it's like you have, if you ignore photons, you have this Coulomb interaction and you have static interactions, right? In general. So in the case of weak interactions, if you ignore the exchange of the bosons, if you ignore the bosons, you think of them as coming together and going off. Okay, that is when the interaction always takes. Interactions must be local in space and time. Okay, because of relativity, you cannot change the position and time of interaction simply by going to a different frame. So if you have something exchanged, then you can do that as a relativistic theory, that in one frame there is some exchange going on. In another frame also there is some exchange with slightly different properties. But if you try to ignore that, which you can at low energies, sufficiently low energies, the exchange energy is so small that you can ignore what is being exchanged, and then you have to think of them as point-to-point interactions. So then it's like one current coming in, another current coming in, they interact and they go off. Okay, current is a 4-dimensional current. Okay, so both charge and current density. So for the case of, sorry, you have a question?
Yeah, I do.
Yes.
So, in the fourth point, you have written the particle antiparticle in the second bracket. If and what is the significance of writing them as if?
It is funny.
Some final whose wave function you can.
I have just written this.
Yeah, so I mean, that was quite okay, but why write?
New E,
The expression.
New E, F, F.
Oh, sorry, you have just
Yes.
written the basis.
Yes.
Okay, yeah, great.
And the looked up sign.
And the gamma mu and the gamma matrices.
Yeah,
Gamma mu and the Dirac gamma matrix.
Dirac equation.
Dirac gamma matrices. Yes, because this is the current. This is the
That's right.
current of neutrinos. This is the current of the fermions. Okay, and this is something that is important, but not for this part does not get into the explanation for this. Is that this weak interaction? This is an important contribution of Salam. That this weak interaction is between left chiral particles. So if you think of massive particles, they all have spin, right? So these all fermions have spin. All fermions have spin half or something else, but all the known fermions, all the known elementary fermions have spin half. So if they are massive, you look at them moving, okay? And then if you look at their spin, either it is right-handed rule or it's the opposite of that. If it follows the right-handed rule, then it's called right chiral, okay? Right helical, actually, not right chiral. Somebody's going to kill me. Somebody's going to kill me if I said that. But yes, no, there is a reason why I said that. Chiral means handed.
Yes.
Okay, chiral means handed. This is a Greek word. Chiral means handed, but this handedness is related to the helical property. If it is massless, then the helicity is the same as chirality. But if it is massive, you can still define a chirality, but if it's massless, you cannot define helicity. But what you can say is that if you look at massless particles, if the spin is along, massless particles are always moving at the velocity of light, right? So if they're also spinning, if they're fermions, if the spin is along the direction of motion, it's right chiral. If the direction is opposite to the direction of motion, they're left chiral for massless particles. For massive particles, you can break them up into right and left chiral components, but they're not independently. I mean, the helicity is not the same as chirality because you can bring them to a stop. And even then, something called chirality can be defined, but helicity cannot be if they're not moving. Anyway, so it's, I don't know. Chirality is handedness. Anyway.
So you have about 10 minutes.
Oops. Okay, so I'll finish quickly. So at ordinary densities, so this is what I should have come upon here. So at ordinary densities, I'm writing this, as I said that I'm not writing this in terms of Lagrangians or Hamiltonians, but in terms of equations. So this is the interaction term in some basis. And if I look at the ordinary densities, I can replace the second term, this bracket in the second term. I can replace that by the average in the Hamiltonian. Okay, there is no self-interaction. The neutrinos are not interacting with themselves. So whatever happens to the background fermions does not directly affect the neutrinos. So I can replace the background fermions by their average current. by the current, by the classical kind of average, okay? Almost classical average. And then I can say two things, that this W plus minus exchange has to take place only with charged electrons, because there's a charge, right? So at each point wherever there is exchange, charge must be conserved. So if there is a charged electron on the other side, I can have an exchange of a charged particle. Otherwise, the charge goes from the neutrinos, and where does it go? Or it comes to the neutrinos, where does it come from? So on the other side has to be a charged electron. So therefore, remember that the electron neutrino must have an electron with it, because it's a doublet. Wherever the electron neutrino is, there has to be an electron as well. So it will have a charged interaction with the electron. But other neutrinos, other flavors of neutrinos, they will not have charged interaction with electrons. Okay. Matter has only electrons. Matter does not have muons and tau particles. It has only electrons. So with electrons, only electron neutrinos will interact, not the tau and mu particles. So if whatever comes from the sun has become muons and tau, they are not going to interact with the electrons that are in matter, not by charged interactions, but they can interact by the neutral current, neutral boson interaction. Okay, so they can interact by exchanging Z or gamma, and all electrons can exchange Z or gamma with electrons, protons, and neutrons. All neutrons can do that. But then the contributions of electrons and protons cancel. I have not shown that, but it's a little more complicated than this showing here. But they will cancel, and only the neutron contribution will remain. So these two have slightly different values. Okay, electron and proton cancel because electron and protons there are the same number of electrons and protons in ordinary matter, because ordinary matter is uncharged. So that's why the contributions are opposite, so they'll cancel. And then in the Schrodinger equation, when I write, so this is the advantage of using 2 by 2 matrices, and because 3 by 3 will have 3 by 3 here and a 3 by 3 here, and I will be able to tell you what it is. So in the mass basis, you can look at the second line. That is what the Hamiltonian looks like. Okay, so this is my flavor. This is what takes it to the flavor. I have the diagonal interaction in the flavor, and then I come back to the mass basis, and the remaining part is diagonal in the mass basis. Okay, because I'm looking at the Schrodinger equation, I have to look at the Hamiltonian where it is diagonal. Otherwise, I cannot solve this directly. Right. So this is the trick of doing that, and then I go to the flavor basis. Okay, so earlier I had time. You can always ask this question. I have ddt here and I have ddx, and that is because the neutrinos are traveling close to the speed of light. So time is basically distance. Okay, so I can change time to the distance traveled by the neutrino. Time traveled and distance traveled are essentially the same. So that is why I have replaced ddt by ddx. And here, what I have done is I have multiplied by u dagger on the left, and this becomes the flavor basis, and u dagger is here. So I have gone from diagonal in the mass basis to diagonal in the flavor basis. So then I have just broken this up. So if you look at this carefully, you will see that this is exactly right. Okay. And this is very simple algebra, nothing else. And for two flavors, as I mentioned, that this is just a rotation matrix. And this calculation is slightly more complicated. So just from here, you can solve this. You can solve this, calculate, mu e going to nu mu means that I have to find the time dependence or x dependence of nu e states and take the projection on nu mu. That is what I wrote earlier, right? Nu mu on the left and nu e of t on the right. That will give me the probability, that will give me the transition amplitude, and this mod square of that is the probability, and this L comes from the distance. So that is like time. L by C is the time. Okay. GF has a constant, GF has a Fermi constant.
Weak interaction constant. Weak interaction also.
The Fermi constant.
মানে গ্র্যাভিটেশনে যেমন জি সেখানে
Electromagnetic constant কি? Alpha. 1/137. Weak interaction of the GF.
কিন্তু আলফাটা হচ্ছে dimensionless, আর এইটা হচ্ছে ডিমেনশন ফুল,
dimensional.
এটা একটা ডিমেনশন,
যেমন GL
exactly, not from the same reason. But anyway. So if you calculate this probability, I mean, this is, you have to calculate this. I cannot just show this. I'm just showing this, that there is a probability like this. The important thing is, if you look at this, then you see that as L changes, as the distance travel changes, this oscillates. This is not a constant. So as you change the distance where you are looking at this will change. The probability will change. The probability of finding the mu1 neutrino in what was originally an electron beam will change. It will go from something very small, actually something, it will go from 0 to something much larger, usually. Okay, not necessarily 1, because this number is still here, but it will change. Okay, so not all the electrons that started out are going to be there after a distance L. Okay, so that is the solution of the solar neutrino problem.
And the delta mm, that is the,
That is just a redefinition of delta m square.
delta m square is mass difference. or-
Delta m square is the mass difference.
Square is the mass difference square in matter. Because
Yes.
this has to be again, if
This
it
is
is transformed to mass basis in the matter.
Yes, here is the matter. This is the matter effect. This matter effect came from the this matter effect came from the neutral current interaction. This came from the charge boson exchange. Okay, so altogether, this neutral boson exchange is for all the neutrinos with all the matter. So that is because it's for all the neutrinos, it will come out.
So delta m square is just the mass difference.
That's the mass square difference.
Mass square difference in vacuum.
This
Now
is in
this
matter.
is what you see in matter.
This is what you say. Okay, so you can see that there is an oscillation because of this.
It become equal when your A is equal to 0.
When I is দুটো নিউট্রিনোর মাস m square 1 2 লিখেছিলাম আগে, m square 1 m square 2 বা m1 m2. So delta m square is m square 2 minus m square 1. Okay. হ্যাঁ, ক্যাপিটাল এ মানে হচ্ছে ইন ম্যাটার। স্পেসে আমি এইখানে চেঞ্জ পাবো না, এইখানে আমি দেখতে পাবো, আমি ওইখান থেকে ক্যালকুলেট করলে কিছু একটা আসবে।
না না, তোমার তো ওটা তো ফ্লেভার বেসিসে হলো তো, কিন্তু তোমার তো প্রপাগেট করা তো মাস বেসিসে। তারপরে ম্যাটারের মধ্যে ফ্লেভার বেসিস করতেই হবে, কারণ ইন্টারঅ্যাকশন রয়েছে, ফ্লেভার জানতেই হবে, তাহলে যোগ করতে পারবে না। এইবার এটাকে আবার ইউনিটে ট্রান্সফর্ম করে মাস ম্যাটারের মধ্যে মাস বেসিসে আনো। ম্যাটারের মধ্যে মাস বেসিসে আনলে ওই cos θ sin θ cos θ m sin θ m হতে হবে, সেইগুলোই দেখো উনি লিখেছেন তলায়। ওইটাকে ডায়াগোনালাইজ করা মানে tan 2 θ m।
না, একটা জিনিস আমি যেটা বলবো, যেটা হবে ম্যাটারের মধ্যে এই জিনিসটা রয়েছে, রাইট? আমার যদি ম্যাটার না থাকে এটা 0 হয়ে যাবে,
তাহলে ওইটা একই equal।
তাহলে ডেল্টা এম স্কোয়ারটা একই থাকলো। এই জিনিসটা কিন্তু 0 হলো না,
না ওটা না,
এটা কিন্তু 0 হলো না। ম্যাটার না থাকলেও কিন্তু অসিলেশন হবে,
হ্যাঁ।
ভ্যাকুয়ামের মধ্যে অসিলেশন হবে। এই এলটা রয়ে গেল, এই ডেল্টা এম স্কোয়ারটা কিন্তু নন জিরো। মাস থাকলেই অসিলেশন হবে, মাস না থাকলে অসিলেশন হবে। ক্যাপিটাল এটা হচ্ছে ম্যাটারের জন্য আসছে, ক্যাপিটাল হচ্ছে এইটা। আগে যেটা বললাম তোমার আগের পাতায় বলা ছিল যে কোথায়, এই যে সো চার্জ বোসন ইন্টারঅ্যাকশনের জন্য, চার্জ বোসন এক্সচেঞ্জের জন্য একটা এ নিয়ে আসে, যেহেতু প্রোটন আর নিউট্রনের সঙ্গে ইলেকট্রন নিউট্রনের কোনো ইন্টারঅ্যাকশন নেই। চার্জ বোসন ইন্টারঅ্যাকশন, ইন্টারঅ্যাকশন তো কোয়ান্টাম মেকানিক্সে তো আমরা ফোর্স বলি না, ইন্টারঅ্যাকশন
এটা উইক ইন্টারঅ্যাকশন।
সেটা উইক ইন্টারঅ্যাকশন। একে কোয়ান্টাম মেকানিক্স, তাই রিলেটিভিটি, এখানে ফোর্স নিয়ে কিছু বলা খুব মুশকিল। তো যাই হোক, তো ডেল্টা এম স্কোয়ার যেটা, ডেল্টা এম স্কোয়ার এইটা 0 হয়ে গেলেও আমার কিন্তু এইখানে একটা জিনিস থেকে যাবে, একটা অসিলেশন আমার সবসময় থাকবে, স্পেসেও থাকবে। ম্যাটার থাকলে সেটা চেঞ্জ করবে, কতটা অসিলেশন হচ্ছে সেটা চেঞ্জ করবে। তো এটা ম্যাটারের জন্য হবে। ফাইনালি এইটা হচ্ছে মানে আমরা এখন যেটা করছি, আমরা উইক ইন্টারঅ্যাকশনের কথা বললাম, কিন্তু স্পেস টাইমের জন্য আর একটা ইন্টারঅ্যাকশন আছে। Okay, so this comes from considering fermions in curved space-time. So I didn't want to talk about this. This is why took me. I was reluctant to talk about this in a colloquium, because you are not familiar with either of these things. So this is basically looking at the dynamics of fermions in curved space-time. And that is not straightforward. So what you have to do is basically other than ordinary gravitation between matter. So because fermions have a certain kind of, they satisfy Dirac equation in flat space. Here in curved space-time, they generate something called torsion. Okay, space-time torsion. So that is a non-dynamical field, means it does not propagate. Okay, so ordinary gauge bosons like photons and your charge gauge bosons, Z, etc., they have an equation of motion. Okay, you solve the equation of motion with boundary conditions, you find something. Okay, different boundary conditions will give you different things. Different sources will give you different things. The torsion is completely defined by the sources. There is no dynamics. Okay, it's a non-dynamical field. The equation of motion is algebraic. So when you write the equation of motion, you get a solution directly. So the field is equal to some other combination of some other fields. Okay, that is what is called a non-dynamical. Right. So that means you can eliminate that from the action. Eliminate that from the action. Because it is the solution, it is always, the equation of motion itself is the solution. That means you can put it back in the other equations of motion, right? Because it's just a combination of the other fields. There is no derivative in the equation of motion. So you put it back in the other equations. And once you put it back in the other equations, that gives a new equation for the other fields. Okay. So if you do that at the level of the Hamiltonian or at the level of the action, that gives a new interaction between the fermions. The torsion is eliminated and you get a new 4 fermion interaction. So I had an earlier 4 fermion interaction, if you remember, from the effective interaction that came from ignoring the exchange bosons and weak interactions. Here you don't have to ignore anything. This is scale free. This is at all scales. Okay, this is not at low energies. At all scales, I can integrate out or eliminate this torsion field. And then I'm left with effective 4 fermion interaction, which is this. You can see that it's a quadratic square. So it's a 4 fermion. And this sum is over all fermions. Not only neutrinos, not only electrons, not only any specific thing. Every fermion in the universe will cause this torsion when it's put in curved space-time. Every fermion will couple to this torsion. And when I eliminate, every fermion will couple to every other fermion and itself. Okay, so self-interaction is also there. And these lambdas I have written, these are all unknown. Okay, these must be determined from experiments. Okay, so there is no principle or fundamental principle or theory that will produce these lambdas. These are like the GF, but GF, the Fermi constant, after weak interactions were found to be a gauge theory, there was a way of calculating the Fermi constant in terms of other things that we know or other things that we could find out. But here, there is still no way of figuring out what these constants are because there is no universal property that connects all the fermions in curved space-time. In mass basis. In mass basis. Because they are part of the Dirac equation, they appear with the Dirac equation, they are going to be diagonal in the mass basis and not in the flavor basis. So this is exactly opposite to the weak interactions. Okay, and then for neutrinos in matter, this interaction is diagonal in the mass basis, but they have to be in matter because it's a 4 fermion interaction. If there is no background fermion, there's not going to be an interaction. Outside of the fermions, there is no torsion. Okay, so they have to be in matter, and now you will have a new interaction which is diagonal in the mass basis. And as soon as you go to flavor, that gets mixed as well. Okay, like the mass difference, the mass square difference. Now you will have. Okay, I have not written that. So this Hamiltonian is now a new contribution of the Hamiltonian. There are these lambdas which correspond to the 3 types of neutrinos, 3 mass types of neutrinos, and n tilde is a kind of weighted density of the background fermion. Okay, so all neutrinos will have this contribution in the Hamiltonian in the evolution, Schrodinger equation,
তাহলে তো ওগুলো যোগ করার সময় তো আবার এটাকে ফ্লেভার বেসিসে
নিয়ে যেতে হবে,
ইউই ব্যবহার করে
Yes.
তারপরে যোগ করতে হবে।
হ্যাঁ। করতে হবে। এবং তখন যেটা হবে, অন্যটাতে মাসে আপনার একটা 1/2 ছিল, এখানে নেই,
হ্যাঁ, এখানে নেই।
কাজে এখানে একটা এনার্জি ডিপেন্ডেন্ট অ্যাডিশন চলে আসবে, ল্যামডা টাইমস ই চলে আসবে, হ্যাঁ, ডেল্টা ল্যামডা বলে একটা জিনিস আসবে। আমি এখানে ওই একটা ডায়াগোনাল পার্ট বার করে নেবো, আর ল্যামডা 2 মাইনাস ল্যামডা 1 পড়ে থাকবে, তার সঙ্গে একটা ই চলে আসবে। So it will be an energy dependent contribution, okay, and that will affect all these things. And not only all these things, it will affect all fermion interactions, not only neutrinos. It will also affect, you know, this is actually a parity violating interaction, so it will affect parity experiments, it will affect CP violation experiments, and many other things. Okay, typically a neutral current type interaction, there is no charge current. So that's it, and these are based on, you know, these papers.
এস্টিমেট হয়েছে কোনো ডেটা এখনো হয়নি।
হ্যাঁ, কিছু কিছু হয়েছে, মানে আমরা করেছি, এই লাস্ট পেপারটা দেখবেন, এই প্যারিটি নন কনজারভেশন, আর আমাদের এই পেপারটা দেখবেন, এই রিয়ার ইন্দ্রজিতের সঙ্গে যেটা আছে, এই থার্ড পেপারটা। হ্যাঁ, এই সেকেন্ড পেপারটা হচ্ছে কেমন ভাবে এই ম্যাটার ইন্টারাকশনটা আসে। থার্ড পেপারটা একটা ইয়ে আছে আপনার, এস্টিমেট আছে নিউট্রিনো অসিলেশনের উপরে কি কি এফেক্ট পড়ে। এটা হচ্ছে আপনার ডিউন আর জুনো, ডিউনের জন্য আছে, জুনোর জন্য আছে। দেখুন আছে, আরো আমরা করছি, আরো অন্যান্য জিনিসের জন্য করছি। আর এই ফোর্থ যেটা, সেটা হচ্ছে পিওরলি গ্র্যাভিটির জন্য। একটা কোলাপসিং গ্যাস যদি হয়, তাহলে এই ফার্মিয়ন ইন্টারাকশনের জন্য, সেলফ ইন্টারাকশনের জন্য রিপালশন আসতে থাকে। কোলাপসটা ইট উইল বি অ্যাফেক্টেড, বাড়তেও পারে, কমতেও পারে, ল্যামডা গুলো 0 না হলে কিছু না কিছু হবে। সো আমরা দেখিয়েছি যে কিছু কিছু কম্বিনেশনের জন্য দেয়ার ক্যান বি এন রিপালসিভ এফেক্ট, কোলাপস উইল স্লো ডাউন। সো দ্যাটস ইট।
Okay, so there were several questions during the talk. The other questions? Yes.
So I have a question for the neutrino mixing part. So is there any fundamental similarity or dissimilarity between the neutrino mixing matrix and CK matrix, other than the fact that CK matrix works the quarks and this works with the electrons?
Yes,
So
that is what it is.
so but besides this,
They are very similar. And quarks are, you know, genuinely massive. Neutrinos, you have to figure out where the mass comes from. Right, there are right-handed quarks. There are no right-handed neutrinos, as far as you know. There may be, but you don't know them. So
Those unsolved questions like why those mixing levels are so low and here they are so big.
well, if you have this additional thing, that might help in explaining. Yes, because that will change everything.
No, but surprisingly again, theta 1, 2 plus theta 1, 3.
But
Plus
remember,
theta-
those are they're model dependent, right? They did not assume these values of theta 1, 2 and theta 1, 3. They are calculated assuming, or without assuming this additional interaction.
Right.
Okay, so once you take these and let all of them run free,
Then
maybe things will change. You don't know.
No, but there is I mean theta 1, 2
When
plus-
theoretically nobody is stopping you to have from having a large.
But earlier also theta 1, 2 plus theta 1, 3 plus theta 2, 3 is approximately equal to pi by 2. That is approximately maybe I think, but
We don't know.
There is another question. Yes.
I have two questions. I
Sure,
ask
sure.
the first one.
You can ask both. I have no problem.
The time wise, others will be there. So the curve space time.
Yes.
If you go to that slide, am I correct in understanding that the extra kind of, so for example, here is the effective four fermion interaction that is different from flat space time. So is it that has to do with the property of space time, the
Yes.
curvature of space time,
Absolutely,
right?
yes.
But then comes the point that if somebody has to see this effect, like for example, here when we're talking about curvature of space-time, is this like local curvature or is it a global
No,
curvature?
it
of
is a local
space-time?
equation, this Dirac equation.
So for example, if there is a massive object and if I have curvature of space-time, we should be able to have something
It is
like
not
this.
curvature directly, there is no curvature term in this.
Okay. So then, how is the space-time property being incorporated here?
If you have flat space-time, this will not appear.
This will not appear. So that's what I'm saying.
Not flat space-time in that sense, not flat, I mean, we cannot have flat space-time.
Right.
We live in a universe that has gravity,
Yes,
so we cannot have flat space-time.
right.
That is why we have it. But if you were to live in a universe, imagine a universe where which is flat, which has no gravity, then this term will not be there.
Okay,
So
so
which
I
means that lambda value depends on the curvature.
No,
Then how can
lambda
I go
independent.
how can I go from here to
the
the
flat-
locally inertial?
You can, they will always be there, local inertial frame will still have this, that is the point. You can go to the approximately flat laboratory space-time, which is locally inertial. And you'll still have this four-Fermi interaction, there is no torsion here, there is no gravity. But if you did not have gravity, you will not have this. এটা কি বুঝছো?
Oh, so the idea is that it is because of gravity, so we will always have this.
We'll always have this because
Because of
space-time,
gravity.
yes, because gravity is present in.
Okay, but then the other term that we generally use as a four-Fermi interaction,
That is for weak interaction, right?
yeah, that is for weak interactions.
That is defined in flat space-time.
Oh, yeah, that is defined in flat space-time. So this has nothing to do with that thing. That is just a weak interaction you define in flat space-time. And this is an effective interaction that is coming from curvature, from gravity.
But not curvature.
Not
Gravity has two parts. Gravity has two parts. Gravity has one, I mean, if you think of the local Poincare symmetry, one part is Lorentz, one part is translation.
Yes.
Okay, so because of these two parts, you get both your ordinary general relativity and you have this addition.
Okay, so then is there a way that we can, we take this kind of experiments in
Yes.
terrestrial,
Yes,
that
in neutrino experiments, in clarity violating experiments, and CP violating.
so that's the experiment, Dune or something you are talking.
Yes, Dune is for neutrino. Yes.
From where do we get those lambda values, the
Yes.
interaction
Yes.
of the constants?
Yes, but Dune has, Dune is still not functional. But there are other experiments you plan to look into. Yes,
Yes, Ragnik.
I just have a last question, that is, what are the impacts of you have considered that Neutrino is a real particle?
yes.
So instead, if I consider Neutrino is the Majorana particle, so how would the oscillation length and oscillation time scale will be affected?
Probably not at
No,
all.
no, not at all. For
Yeah.
oscillation, nothing will change. Only another phase will come, but that can be rotated away.
I mean, it's not a
Majorana
Majorana
particle.
particle, it's a wild particle with a Majorana mass.
Not at all. Oscillation power will change.
That's all. Yes.
So, yes.
I could see. So that can you simultaneously get mass state as well as the Taylor state?
No.
They don't commute,
No, not commute, they mean, they're not
they are
parallel.
not parallel.
They're not parallel.
So I, yes,
সেকেন্ড না থার্ড স্লাইডে আপনি একটা কোশ্চেন বলেছিলেন কেন থিটা আসছে সেটা একবার বলবেন
কোশ্চেনটা তোমায় বলতে হবে, আমি কোশ্চেন বলেছিলাম বললে হবে না, কোশ্চেনটা তোমায় বলতে হবে, আমি উত্তরটা বলতে হবে।
সেকেন্ড না থার্ড
এটা
অ্যাঙ্গেল আসছে
ও এগুলো কেন অ্যাঙ্গেল?
এটা আপনাকে পড়াতে হবে।
কোশ্চেনটা করা মাত্র দেবাশিসটা বললেন তাহলে এটা পড়াতে হবে ক্লাসে।
হ্যাঁ,
এই ফর্মুলার ফর্মটা তো ওই নিউ1 আবার মডেল চিহ্ন আবার গ্রেটার দেন চিহ্নের মধ্যে ওটা কি
এটা স্কেল বেসিস,
একটা কোয়ান্টাম ফিজিক্সের একটা সার্টেন ফর্মালিজমে এটা
এটা বেসিস স্কেল।
এটা মানে অ্যাঙ্গেল বলতে তো আমরা প্রজেকশন করছি
না
অ্যাঙ্গেল বলতে আমি অ্যাঙ্গেল বলছি বিটুইন 0 and 2 পাই। হ্যাঁ মানে একটা জিনিস আমি বলতে পারি, যেটা সেটা পরে হয়তো ভালো করে পড়াবেন, আশা করছি। সেটা হচ্ছে যে এই U2 U3 এই যে গ্রুপগুলো, এইগুলো হচ্ছে কম্প্যাক্ট গ্রুপ, মানে যদি ওর ভলিউম ক্যালকুলেট করা হয়, ওগুলো অ্যাকচুয়ালি ভলিউম ক্যালকুলেট করা যায়, সেগুলো ফাইনাইট। সেগুলো অ্যাঙ্গেল না হলে ওটা ফাইনাইট হয়। যদি আমার স্ট্রেট লাইন হয়, বা যদি আমার সে R3 হচ্ছে স্পেস, আমি যদি তার ভলিউম ক্যালকুলেট করি আমি ইনফিনিটি পাই। হ্যাঁ, এখানে U3 যেটা যতগুলোই প্যারামিটার হোক সেটা কম্প্যাক্ট, সেটা একটা ফাইনাইট ভলিউম আছে, এটা ক্যালকুলেট করা যায়, মানে হচ্ছে এগুলোকে অ্যাঙ্গেল দিয়ে দেখতে পারি।
তো আরেকটা কোয়েশ্চেন হলো, ওই যে ওই যেখানটাতে আপনি ক্যালকুলেট, I think slide 10 হবে, যেখানে we were calculating the এই যে তার হ্যাঁ এর আগে স্লাইড একটাতে এলো দুটো বার টু জিএফ, they are yes they are proportional to GF, কিন্তু ওই নিচে আর ওপরে দুটো আর চিহ্নটার বদলটা ওটা
ও না, দুটো এক জিনিস নয় তো, আমি ডিটেইলসটা লিখিনি। এটা হচ্ছে চার্জ লেফট অন চার্জ পার্টিকেল এক্সচেঞ্জ, চার্জ মোশন।
ইলেকট্রন ডেনসিটি
হ্যাঁ, এনিটা হচ্ছে ইলেকট্রন ডেনসিটি,
density।
সবকটাতেই আছে
হ্যাঁ।
ইলেকট্রন ডেনসিটি, মানে ইলেকট্রন নিউট্রিনো গুলো চার্জ পার্টিকেল এক্সচেঞ্জ করে কেবলমাত্র ইলেকট্রনের সঙ্গে,
হ্যাঁ।
সেই জন্য ডাব্লিউ এর জন্য কেবলমাত্র ইলেকট্রন ডেনসিটিটা আসবে।
হ্যাঁ।
ওকে, নিউট্রাল কারেন্ট এক্সচেঞ্জ যেটা নিউট্রাল ফেজ বোসন এক্সচেঞ্জ, সেটা ইলেকট্রন প্রোটন নিউট্রন সকলের সঙ্গেই হবে।
হ্যাঁ।
হ্যাঁ, কিন্তু ইলেকট্রন আর প্রোটনটা ক্যান্সেল,
So it's the neutrino, sorry, the neutral one, just the neutral one.
আর স্ট্রেংথটা আলাদা, সেই জন্য
Strength টা।
so when you want to find this
না
আচ্ছা।
অর্থাৎ এখানে নেই।
না 1/3 হচ্ছে অসিলেশনটা হওয়ার ফলে।
Oscillation টা-
ওই যে আমি দেখালাম, এই যে প্রবাবিলিটি দেখালাম, তো এখানে আমি দুটো দিয়ে দেখালাম। তার মানে যেটা ইলেকট্রন হিসেবে শুরু হচ্ছে, ইলেকট্রন নিউট্রন হিসেবে শুরু হচ্ছে, সেটা যখন এসে পৌঁছচ্ছে তখন কিন্তু তার অনেকটা মিউন নিউট্রিনো হয়ে গেছে। তাহলে যেটা দেখা যাচ্ছে সেটা সবকটা ইলেকট্রন নিউট্রিনো নেই।
তুমি যে 1/3 পাচ্ছিলে তার কারণ হচ্ছে যে তুমি মানে তুমি ভাবছো যে সব ইলেকট্রন নিউট্রিনো আসবে, আমি ডিটেক্ট করব, কিন্তু আসলে তুমি 1/3 ইলেকট্রন নিউট্রিনো ডিটেক্ট করছো, কিন্তু আরো 2/3 তোমার মিউ1 আর টাউ নিউট্রিনো ডিটেক্ট করতে পারছো না। যদি পারতে তাহলে তুমি টোটালটাই পারো। I have a question actually. So since you said that if there is no mass, there is no neutrino oscillation. So then, since we have pretty good results of neutrino oscillation, so there is a good constraint on neutrino mass from there.
What are you asking?
I am asking, is there a good constraint on mass from neutrino
What
oscillation?
is the mass?
That's what people say.
না না, মাস এখানে তো ডেল্টা এম স্কোয়ারটা মাপছে, এমটা কিন্তু মাপতে পারছে না, সেটা নিউট্রালের ডাবল বিটাটিকে দিয়ে আমি মাপতে, তাতে তাতে তোমার ইয়ে আছে, বাপার বাবুখানটা আছে।
সেটাকে পেতে হবে তো।
no the base is it's your cosmological measurement.
Cosmological measurement touches to কত?
Five.
Less than
0.5,
0.4 EV বা এরকম কিছু। Delta M 0.4 EV।
No, not delta M.
M
Delta M
M
square.
is less than 0.4
Cosmology M.
হ্যাঁ cosmology হ্যাঁ এটা less than
delta M is much more constrained, I think.
কিন্তু these are all assuming with, মানে not assuming with additional interest.
Not that, you know, those additions.
So take that in and things might change.
না, অসিলেশন হতে পারে আরো